So today we cover section 6.4, which talks about sampling distributions. And you're going to be a little bit sad to see that section 6.4 is a short section. There's not very much homework, but it introduces a really important topic that we'll really spend a lot of time in section 6.5. So 6.4 is going to just set up everything we need to get ready, and then we'll really take a good look at sampling distributions and applications in section 6.5. But first, just to review a little bit here, we've got a few terms here just to review. So the first one is population. Some of these topics are going to come up in 6.4 and 6.5, so that's why we're going to review a little bit here. So population, as you know, is the set of all measurements or observations of interest. And the population can be thought of as measurements or observations for the entire group of objects or people about which information is desired. Okay, and then of course a sample. I'm not sure why it moved like that. Okay, there we go. Sample is a subset of measurements from the population, and for our purposes, the most important samples are random samples. Also in our book, this is just in our book. In our book, when our author mentions random sample, what it means is simple random sample. So it's not true in other textbooks, but in our stats book, when you see random sample, it's implied that it is a simple random sample. Okay, so we talked about simple random samples back in section 1.2. Then there's a term that we used a while ago, you were introduced a while ago, called a statistic. And a statistic is a numerical descriptive measure of a sample. And there's a few that we talked about. We talked about X bar, which is the mean of a sample. And we had little s, which is a standard deviation of a sample. And p hat, which we're going to look at soon. P hat is a sample proportion. So just to get an idea here, got a circle, not one of my better circles, but it'll work. And let's say you work for a polling organization and you want to know the proportion of voters who are going to vote yes on proposal 3 or whatever. So you can't actually talk to every single person who's going to vote, right? So what you do is you take a sample. So you take a sample of voters and you find P hat. So maybe P hat says 46. So of your sample, 46% of them said yes, we're going to vote yes, or we're going to vote yes on proposal 3. And then you would use that P hat, your sample proportion, to try to figure out what P, the population proportion, would be. So we'll talk a lot about these in chapter 7. But for now, we have to just review that a sample statistic is one of these numerical measures of a sample, whereas a population parameter, or just a parameter, is a numerical descriptive measure of a population. So an example of that could be mu, sigma, and p, which are these just when you apply them to an entire population. So remember, we have sample, statistic, population, parameter. So, all right, what else do we have here? Often we don't have access to all the measurements of the entire population, which we talked about earlier. So in that case, we take measurements from a sample instead. Then we use a sample statistic such as X bar, S, or P hat to make inferences about a corresponding population parameter like mu, sigma, or P. So we're getting ready to start using statistical inference. So that's when we're going to have information about one of these sample statistics, and we're going to try to infer things about the corresponding population parameter. And there's some of the types of inferences we'll use will be estimation. And this is where we estimate. We estimate the value of a population parameter. And this we will take a look at in Chapter 7. So in Chapter 8, we look at hypothesis testing. And this is where we formulate a decision regarding the value of a population parameter. And this will come up in Chapter 8. This will be an important chapter for a lot of you guys, especially if you're going into the social sciences or psychology. In these areas, typically, even as an undergraduate, you'll look at a lot of research, and especially if you go into grad school, but you look at a lot of research papers, and they will use a sort of hypothesis testing where you're going to end up getting a p-value. And pretty much all modern research now uses these p-values. So we'll look at these p-values in Chapter 8 and learn how to read a lot of research papers and see what the conclusions are based on the p-values. So for some of you, this will be a really important chapter. Actually, I mean for everybody generally, but some of you will really use this a lot after this class. And then we come to regression, which will be familiar to some of you. This is where we make predictions or forecasts about a statistical variable. And we do this in chapter, can you see the pattern? 7, 8, 9, Chapter 9. So this will be familiar to some of you if you've done linear regression. Sometimes linear regression is taught in algebra class. So it'll be, for some of you, it'll be a repeat, but then we definitely are going to go into more details than you would have done in an algebra class, but it'll be somewhat familiar to some of you. Okay, so before we can do any of those inferences, we need to know what a sampling distribution is. So a sampling distribution is a probability distribution So we already know what these are, right? We've worked with probability distributions. They just show how probabilities are distributed. But it's a probability distribution of a sample statistic based on all possible simple random samples of the same size from the same population. Now the sampling distributions that we're going to look at, I'll just mention up here, will be X bar or P hat. And there are others, but these are the two most popular ones, and these are the two that we're going to look at. So We study sampling distributions for the mean, x bar, and also for proportions, p hat. These will form the basis for our work with estimation in Chapter 7 and hypothesis testing in Chapter 8. And these are inferential statistics methods. So the book has an example of the X-bar distribution, the sampling distribution, and it's actually one of the best ones I've ever seen. So I like to use the book's example. And also it's got 500 pieces of data all on one page, and it's just easy to follow and to figure everything out. So what you'll want to do is take a look at this. Well, let's say this. So on page 315, here's what this is. I'll give you the background. So we've got this this little town that has a children's fishing pond, and kids can go and fish here, and they can only keep 5 fish per day. So what they did is they have data from 100 kids. Each kid caught 5 trout, and they measured each of the trout. So on the next page, on page 316, they have a table where they have it all filled in. So if you've got the book, look on page 316, and otherwise I'm going to show you a picture of it also, because you really need to see it to make sense of this. So here's the page, and just let me point out a few things. So see, they've got these samples, sample 1 through 50, and then sample 51 through 100. So there's 100 kids here, and then these are, so this sample number 1, this kid here, here's the length of his or her 5 trout, and then they have the sample mean. So notice they say X bar, because it is a mean, it's the mean of this sample of 5 trout. So this first sample has a mean of 10.8. The second sample, this other kid, the mean of those 5 trout is 9.8. These are all in inches. And then so forth, so you can see all the way down here. So we've got really a lot of data. There's data from 500 samples. Each sample is size 5. And then this column here and this column here is a whole bunch of sample means, right? Each one of these is a sample mean of 5 trout. So we're going to talk about this sampling distribution. So we're going to actually look at the distribution of these sample means. So let's take a look at this. We've got this population right here. Think of this as representing all the lengths of all the trout in that pond. The entire population is here. Just think of it just like thousands of numbers in this pile. Each number represents the length of a trout in the pond. And we do know this. We do know that the mean is 10.2 inches and the standard deviation is 1.4 inches. So if we were going to plot the X distribution, so let's just say we've got this X distribution. X is a random variable. It represents the length of a trout, right, out of all this population. So let's say we just randomly choose numbers out of this population. We just pick numbers out of here, which basically would be lengths of individual trout in that pond. And so let's say we line them all up here on a number line. So let's go, say, from 8, 9, 10, 11, 12, 13, 14. And so this X distribution, remember X is a random variable. This just represents the length of trout in the pond. And to get started, I'm just going to look at these values right here. So looking at this first sample, we've got 11, 10, 10, 12, 11. So I'm just going to put those down on the line here. So we've got, let's see, we've got sample 1 has 11, 10, 10, 12, 11. And then we could keep going down all of these, and basically, I mean, these are just samples, but these samples came from here. So what we could do is plot all of these values in the entire pond, and this is the X distribution, right? This is just a random variable X represents the length of trout. Okay, we're sort of used to this. This is what we've been doing so far. So this would be, if we were making a little graph here, this would be the length in inches, and this could be like a dot plot, right? We could just take all the thousands of trout lengths and plot them on a number line here, and then we could see what happens. Are we going to get a bell-shaped curve, or is it going to be skewed? You know, so we can answer those kind of questions, but this is the X distribution, right? The X distribution. Now what we're going to do over here, though, these numbers here, these means, these X bars, over here, we're going to look at what's called the X bar distribution. I'll just write it out. X bar distribution, this is the X distribution. So this is just the distribution of all the values in the population, but we're also going to show the distribution of values from these two, right? Not only these two, but all the possible samples of size 5. So where this is going to be the distribution of actual X values, raw data, this is the distribution of means of 5 trout, right? The X bar distribution is the distribution of all these means. Not only these 100, but all of the possible samples of size 5. So now if we look over here, and I count off these first few, well, let's get the number line ready. So we've got 8, 9, 10, 11, 12, 13, 14. So we start putting these here. So we've got a 10.8, we've got a 9.8, got a 10.4, 10.6, yeah, okay, I did those in other order. All right, so these are not to scale all that well. But basically we could do the same thing that we did over here, right, with the X distribution, but we're doing it with the X bar distribution. So here's what we're going to notice, though. The X distribution, if you look through the pages here, you will occasionally see a 14-inch trout. Every once in a while, there's just a few of them, but one of these kids is going to get real lucky and catch a 14-inch trout. So over here, there will be occasionally a dot on the 14. Here's the big difference. The X bar distribution, how common do you think it would be to see a 14 as the mean of 5 trout? And that's going to be extremely rare, and maybe it would never even happen. Because think about, if a 14-inch trout is really rare in the population, how likely is it that somebody would get a mean of 14? Right? They're going to be very unlikely, because whichever kid occasionally catches a 14-inch trout, he or she also has 4 other trout that get averaged in, right, to make the X bar distribution. So the X bar distribution typically is going to be, if this is a bell-shaped curve, this is going to be a much skinnier bell-shaped curve, because the variation is typically going to be less here, because any extreme values like a 14, if you get a 14 over here that 14 is getting averaged in with 4 other trout, so it's probably not going to be, by the time you take the average, it'll get pulled more towards the mean. Right, because this X bar distribution, this is a distribution of averages, a distribution of means of 5 trout. Right, so the standard deviation here is going to be smaller. These are not going to vary as much, because the extreme values here on either end will tend to get averaged out because they're going to be averaged with 4 other values, which are not likely to have them all extreme, right? So, whereas if this does have a bell-shaped curve, this will have a skinnier one. The standard deviation is going to be smaller on the x-bar distribution because this is a distribution of averages. And when you take averages, the extreme values get averaged out with the other values. So hopefully that makes sense. So what we're going to find out is that in this case, this will also have the same mean. This mean is also going to be 10.2 inches. We'll find out that when we have the next distribution, whatever the mean is, the x-bar distribution has the same mean. What's going to be different, though, is the standard deviation. The standard deviation of the population, the standard deviation over here is going to be smaller. You're not going to have as much variation because the extreme values get averaged out. Okay, so that idea is what we need to go forward in section 6.5. So take a look at 6.4. There's not a whole lot of homework. 6.4 is basically getting a setup for 6.5. So we just have to make sure that we understand the difference between the x distribution, the distribution of a random variable x, and the x-bar distribution, which is a distribution of the means of, in this case, 5 of those random variables. Okay, so one last way to think of this, the x distribution, this, if we plotted these, we would have all the data points in the population be plotted here. The x-bar distribution is the means of all the samples of the populations. And in theory, it's the means of all of the possible samples of the population. So like in this case, it would be, if we really plotted the entire x-bar distribution, it would be every possible combination of 5 trout from the sample plotted here. Okay, so x distribution, all the data points in the population, x-bar distribution, the means of the samples of the population. So that's what we need to know for 6.4. So try the homework in that section. It's a short section. It's basically getting us ready for 6.5. And if you have any questions, let me know.